Hello guys and welcome to this video. So today we're going to look at the expectation maximization algorithm. This is one of the core algorithms which stays in the backbone of a lot of machine learning solutions. And we will look at this algorithm in an intuitive way, as intuitive as possible, because I think this algorithm may be a little bit hard to understand when you just try to look at the formulas. And there is maybe a lot of maths that will come off as hand wavy in my explanations, but the goal here is not to do some kind of rigorous mathematical proof of why this works, but just get you an intuitive feeling and hopefully get you in a good enough understanding of the algorithm so you could implement it into one of your own projects or one of your own solutions. Okay, and before we start, I thought I would just show you a little bit of how a typical problem that the expectation maximization algorithm can solve would look like. So what you have here is an image of three data sets here, but we don't know that these are the data sets, right? We just have samples, and we have just thrown out three multivariable Gaussians here, which we initialize the parameters randomly in this area. And now we want these Gaussians to sort of find their way and wrap around these data sets, right? Because to us as humans, it's quite easy to see that there is indeed three very nice clusters here that could definitely have come from three different Gaussians, but the algorithm has to find this out by itself. So let's look at this example where these Gaussians find their way in 4 iterations basically. So we started out like something like this, and after iteration 1 we have something that looks like this. So we see that it is already getting good on its way towards the clusters, and on the 3rd iteration we have this, and then 4th iteration we have this. So we see that this is basically converged now. We are wrapping around the clusters really nice and tight. So this is the algorithm. Okay, so let's start looking under the hood and see what's actually going on here. These are the two mysterious steps of this algorithm, the expectation step and the maximization step. And there's a lot of various like formulas on how this should actually be implemented, and they are usually bogged down with a lot of notation. This is the most clean example that I could find, which has the best notation, at least according to me. But there is still a lot of notation, but we will see that this will not be so hard to understand once we dig into the formulas and get to know what they're saying and where they come from. Okay, so when it comes to the expectation maximization algorithm, I think it's good to understand what we're given in terms of knowledge, assumptions, and data, and what the goal is of the algorithm before we start. So the core idea is that someone has given us a sample of xi's, that is data points, that we're assuming are coming from some number of Gaussians. Let's say we're assuming 2 Gaussians in this case for simplicity. This means that we hope to find these 2 Gaussians, which is the goal of the clustering algorithm. There is something that we really have to emphasize on here. The assumption is that we have 2 Gaussians and we don't know their mean and covariances. We're also assuming that they generated the data points, the xi's, that we are given. So let's begin with the expectation step here and see what are these formulas saying. This is the multivariable formula for Gaussian, and this may seem very complex or complicated if you haven't studied multivariable calculus or more advanced statistics, but I can assure you we will not have to think about so much about what this function is actually saying, but to understand this algorithm. But we can just say quickly that what this function can do is that given the parameters that define the Gaussian, which is the mean and the covariance matrix, and a certain point, it can evaluate the probability density function for this Gaussian at this specific point xi. And this is can loosely be interpreted as the probability that that xi was coming from this certain Gaussian. And this is good, right? Because we will try to find these means, the means and the covariances for, in this case, the two Gaussians, which maximize for the points that belong to one of the Gaussians. We want to maximize this probability for both of the clusters. Okay, so this is the normal distribution. Let's go into this formula then. This is where we start to look a little bit into the actual algorithm. What we're having here is basically just the normal distribution evaluated for the points. But there's a little thing here called pi c. And this is a value between 0 and 1. And it says what the prior belief is for the underlying distribution. So let's say that we have various xi's. Someone has given us a sample of xi's, right? And we know that we're assuming, we know maybe that, okay, but probably like 70% of these points should come from one Gaussian and 30% should come from the other Gaussian. Let's assume we know this beforehand. Then we can encode it in this parameter pi c. Or in most of the cases, maybe we don't know this, and then we will just initialize it as 1 divided by the number of clusters. So we say it's equally likely that this point is coming from that cluster and that cluster. So in this case, this value would be initialized to 1/2. So what we will do then? Well, we will evaluate for each sample point xi what the probability density function, given these parameters that we have just found for this specific cluster, was the value of the probability density function up here. And we're expecting high values if this point really seems to be coming from this Gaussian or a cluster defined by these parameters, and we're expecting low values if this xi doesn't seem to be anywhere near the Gaussian as defined by these parameters. And down here we have this sum, which is like the sort of like a normalization factor in a sense, because we know that the xi will have to come from some of the cluster, right? It's not unaccounted for, and that means that if we sum over xi evaluated for all of the clusters that we are having available, or the Gaussians, then we will have some value here which says the actual probability that xi is coming from this certain cluster. Okay, so if xi really seems to fit in this certain Gaussian given these parameters, then we will have that term down here as well, right? And they will and the rest of these one will be low, and then they will sort of cancel out, and we will be left with a 1. So the maximum value here is 1, and the minimum value is 0. If we have a very bad fit here, we will divide by, and some of the other Gaussians may have a much higher probability density function value for this xi, and it will completely dominate here, so we will get a 0. Okay. So what I've done here for you guys is actually I've drawn out an example. So let's look at it. This big piece of these big vectors may make it simpler. With all the notation going on, I always like to draw it up like this. So let's look at this. This is what we will get when we evaluate this function for all the xi's and for all the clusters. In this case, we're working with 2 clusters, right? So we plug in the term x1 into this function. We divide it by this sum. It's going to be the same sum for all of the xi's that we're plugging, or for x1 here, the sum's going to be the same for all the cluster evaluations up here. So we get a value out here, 0.4 for example, and we will plug in x1 again, but with the other cluster that we also have the parameters for, or the other Gaussian, let's say. And we will evaluate this function again, and we will put the result down here where it says R21, which indicates, okay, this is the R value for cluster 2 and 0.1. And we're using 1 indexing here. I'm sorry if you don't like that, but yeah, that's the case. Anyways, so we can continue. We will take the next sample point, x2. We plug it in here. We evaluate it for the cluster 1. We divide it by this sum, and we put the result here, and we continue like this. Okay, so that's what all this notation is trying to say. And I think it's nice to look at what's the like expected result here. We are expecting to have a vector of the same length as the sample size, and with values between 0 and 1 in each of these cells, right? Okay, so how is this helping us, and why is it called the expectation step? Well, loosely, we can interpret this as the expectation that this certain point would belong to cluster 1, and the expectation that this certain point, x1 point, would belong to cluster 2. And in this case we see that, okay, it seemed to be a better fit for cluster 2, and then we have a higher value here, right? But we still see that since we're working actually with probabilities, they sum to 1, right? Because we know that it has to come from one of the clusters. That's our underlying assumption here. And we see that they're also summing to 1 here for the sample x2, 0.7, 0.3, and so on and so on. Of course they do. I have drawn this, but this function actually guarantees that, or this probability evaluation actually guarantees this. But here comes the smart thing about this algorithm. So if we have a really high value here, it means that this point was a much better fit for this Gaussian, the Gaussian 1, than for Gaussian 2 in this example here. So let's say we can say then, okay, then you will have 0.7 voting rights when we're trying to update the new parameters for this cluster 1. Because this point seems to be very happy, but can it become even more happy if we can use this point to update the parameters for cluster 1? So that's the intuition. So let's, instead of interpreting these as probabilities, let's interpret them as voting rights. So we see here that the point here, x2 for example, we will say that, okay, your total voting right is 1, but you can choose how you want to use your voting right when we're updating the parameters for the various Gaussians later on. And this value here, 0.7, means that it will use quite a lot of its voting right when we're updating the parameters for Gaussian 1, and a little bit less of its voting right when we're updating the parameters for the Gaussian number 2. And over here we have a more of the extreme case. Here it says that, okay, this one point is like really bullseye in the middle of this Gaussian, and it will use its entire voting right to make sure that this Gaussian does not move anywhere. It really wants to influence this Gaussian to stay the same way because it's really happy to be in that cluster. So it gives all its voting right here, and this one is 0. And an important thing here actually is that if you have been studying this subject and you have come across the k-means algorithm, That is, at least to me, a lot simpler to understand than expectation maximization in this general case. But actually, the k-means algorithm is doing exactly this. Then instead of saying that okay, okay, this sample point can have various voting rights for updating the various means in the k-means algorithm, instead we're saying no, this point can only influence the mean for its closest mean, right? So this is actually something that can really help you to understand this algorithm, is that we sort of divide, like we give the points the ability to vote not only for its closest and best fitting Gaussian, but it can also vote a little bit for a Gaussian that's not 100% fit. Okay? And if you understand this intuition, then the rest of this algorithm will become very easy for you to understand, I would say. Because then we can start to interpret the points as in terms of their voting rights instead. So, and that's what we're gonna come to here in the maximization step. But let's first look quickly, what does this row actually sum to here? It sums to, this is 1.1, right? 1.3, 2.3. And these points sum to 1.7, right? And the sum of this, all of these values, is equal to 4, right? And we know this because we have 4 points and they have 4 voting rights. So the sum of these values should equal to 4, right? Because the only thing we did was we divided the voting rights among the points. And this is how we can from now on interpret these points in terms of their voting rights. So when we go into the maximization step here, we have these scary looking formulas. But what we're actually saying is that we have MC here, and that says, okay, let's sum these values for this certain RC equals to 1 for that cluster and all its values, that's all it's saying. And we do this and we get what's the number of voting rights that are active for cluster 1, and the same one for, and we do the same for cluster 2. So that's the value of MC. So M1 is equal to here 1.1 plus what did we say? 2.3, right? Something like that. And that's the amount of voting rights that's active for this certain cluster. And to update the priors now, let's assume we did not know anything about them. Then we say that it makes sense, right? That the points that want, like this, the total number of voting rights for a certain cluster divided by m here. M is the number of samples which we earlier said was equal to the total number of voting rights. That could be a good indication of the priors, right? Because if there's a lot of points coming from a certain cluster, they will all use a lot of voting rights for that cluster, and that means that we can assume that the prior for this cluster should be higher. But that's a little bit far stretched, but I think if you think about it, the intuition could say that it sort of makes sense. Okay, so now we're actually coming to the end here with the two most crucial parts, like really the core of the expectation maximization algorithm, and that is, how do we update these mean vectors and covariance matrices for the clusters, given that the points have decided what their voting rights should be. And this is important to understand where this comes from. And the intuition here is that if we have just, let's forget about clustering for a little while here, and we just think, okay, we have a sample and we just want to find the Gaussian which fits the sample the best. This is like a general problem. How do we do this? How should we choose these parameters? Well, it turns out that you can do something called maximum likelihood uh, estimation for this. And this is another subject that's really interesting. But the point is that there is falling out from this using like derivative and maximizing this like log likelihood um, and this mathematical procedure of the ML uh, estimation, we can derive that the way to update this mean is this formula here. So like how this formula is derived, that's another subject for another video. But the important thing is that there is a mathematical way to find the best mean and the best covariance matrix to find a Gaussian which can fit a certain distribution. But that formula does not exactly look like this, because then we would have 1 divided by the number of samples, and this RIC would not be here. So we would just sum the samples, divide by the total. So that's like basically the definition of the mean. But it turns out this is also the best ML estimate for the Gaussian. But now we have started to interpret the points as their voting rights instead. So sort of that the point is not exactly its entire self for each cluster, but only part of the point should be considered when we're updating a certain mean or a certain covariance for a certain cluster, right? And we said that this value MC says what's the total number of voting rights active for this certain cluster. So this is basically the good old ML estimate of a mean for a Gaussian, when we take into consideration that each point does not have the sort of right to actually contribute when we are doing this ML estimate. So how this is interpreted is that the point is using some of its power for each of the Gaussians that should be updated. Okay. And this is exactly the same idea here, that okay, if we would have a big N here and no RIC, this would be the ML estimate for a general sample. But now we are not looking at the sample as in 100% effect. We are saying no, you cannot do what you want to do, you can only use your voting right. So we will weigh each of these evaluations with the corresponding voting right for the point. And that is how we update the cluster parameters. So this is one iteration. So in the first iteration we have just initialized the mu-c and the covariance with some reasonable bounds for what we think they could be, but it's like basically completely random. And we do one iteration of this algorithm. Now we have a better way to update these parameters, which we have found by evaluating this function up here and find how much the point thinks that it wants to influence these updates. And this is basically the entire algorithm. Then we just iterate, and now we have updated the parameters for the clusters, right? So we will use them when we do this step up here. The new RICs will be different. Hopefully the points that were really like good fit, they will have even higher values now, because hopefully we have shifted the Gaussians in a way that suits them. So yeah, that's basically the algorithm. And does this converge? Why does this work? Well, that's an interesting subject, but it has been proven that indeed this algorithm will converge for the general case. But that's not something we will look so much into now, because this is more to understand the algorithm as a concept. So I think the most important thing here is that we really realize that we're giving the points the voting rights when we're going to update the parameters, and it's coming from how good it already felt that it was to one of the Gaussians. Okay guys, that's the video for today. I hope you enjoyed the video and that you will learn, or at least got a little bit more intuition about how this algorithm works. If you're interested in how this can actually be implemented in Python code, be sure to check out my other video where I am implementing this from scratch using Python.